Good to be here. Thank you very much for joining us. So we're here to talk about what is arguably one of the most consequential technologies of our lifetime, fusion energy. So I'm joined by Francesco, who's the CEO and co-founder of Proxima Fusion. Proxima is also arguably, I think, one of the fastest growing European companies today, and certainly the fastest growing fusion company globally. So Francesco, before I jump in with too many questions, can you maybe, for the benefit of the audience, tell us what the hell fusion is?
What's this thing? Yeah, fusion is the process at the center of every star. It's fundamentally one of the key energy sources of the universe. It's what's giving out the sun and the rays of light that we use for photovoltaics. We're trying to access that source of energy, not so much just at the distance, but really building a fusion, a sun in the laboratory. Doesn't sound so easy. It is not so easy. Yeah. We've been chasing that for a good number of years, several decades, and now we think we are quite close to actually making it into a commercially realistic.
And actually, on that point, so in the last couple of years, there's been a number of significant technological breakthroughs. There's a lot of excitement from investors, particularly like myself. Some $17 billion have gone into private fusion companies in the last couple of years. Last year, $3 billion. There's now 3 companies that have announced their plans to go public this year, maybe a few more in the next couple of months. But at the same time, there's still a lot of skeptics about fusion. And there's this running joke about, for the past 50 years, fusion has been 30 years away, and it's always 30 years away for these people. Mm-hmm. So what is it? Is it still 30 years away, or are we going to get a bit sooner?
I think it's good to be skeptical. Every time you look at something that is of this scale, if fusion, rather than when we will access fusion on Earth, it'll be a pretty big deal. This is the ultimate source of clean energy for humanity. There is nothing coming after fusion. So we're talking about accessing the most energy-dense source of energy that we will ever have as humanity. Now, with that come a number of big claims, as you might expect. So I like to say that fusion is not really a technology, it's a physical process. It's a process that you can harness with a number of technologies. So there are now more than 50 fusion companies around the planet, quite a bit of private money that has been raised. Governments have been investing in fusion technology for 60 more years. And when you look at that zoo of solutions, a bunch of things are not so reasonable, a bunch of others I think are very promising. If you look at the last 20 years or so, we've made incredible progress on magnet technology, on laser technology, on supercapacitors, a number of enablers that fundamentally change the way you look at this technology. Now, if you have a really big hammer, the fact that you have a big hammer doesn't mean that you can mold anything into what you want. Yeah. So we got some really big hammers. The magnet technology that Proxima is leveraging and building more on, they're transformational. We're talking about superconducting magnets, so really complicated, really powerful things.
Maybe just for the benefit of the audience, do you want to explain why magnets are important for fusion?
So what we're working on, as was mentioned, is called a stellarator. A stellarator is a donut-shaped device with magnets that try to confine hot ionized matter. We call that a plasma, effectively star stuff. And this star stuff has to be at 150 million degrees. That's about 10 times the center of the sun. Sounds a bit hot, and it's not terribly pleasant for any material to hold that kind of stuff. So what you do is you hold it in a vacuum, effectively, and you levitate this hot ionized matter. And you do that with magnetic fields. So this hot ionized matter follows magnetic fields, so you create a magnetic cage, a magnetic bottle. And the stronger the magnetic fields that you can create, the better that confinement. So effectively, you need to make sure that no plasma is touching materials. And we've been working on what are called high-temperature superconducting magnets. These are not very high temperature. They're 20 Kelvin, so minus 250 degrees. But they have matured enormously, and they're now at the face of us being able to have a supply chain that is diversified across the planet, that we can build our technology on top of. And Europe is the best place on the planet to do that.
Yeah. And actually, so one of the things as an investor that we're quite excited about, the last 70 years, fusion was in a kind of R&D phase. But just in December 2022, the Lawrence Livermore National Lab in California managed to finally crack the physics. We actually managed to reproduce the effect of a star on Earth in a contained reactor. and produce what is called Q greater than 1, so more energy coming out than energy is used to activate the reactor. And so for investors, that's always very exciting, because when you de-risk the physics, then you move kind of in the next phase, which is the slow commercialization phase, which is mostly an engineering challenge. And engineering challenges with money, talent, and a bit of time is a walk in the park, potentially. And so that's why we're quite excited. But so, Francesco, you maybe to make it a bit more personal for the people here, if you could just tell us a little bit about your backstory, why you launched Proxima Fusion in Munich, Germany, and is Europe actually a good place to build a fusion company?
Yeah, so I've been working on fusion for more than 10 years, give or take. I started in a lab at Imperial College that was working on a thing called a Z-pinch. So a system that takes lots of current, dumps it into a small target, tries to implode it, and then explode it via fusion. Pretty fun. Doesn't really work as a power plant, it turns out. I moved on to what is called a tokamak, which is also a donut-shaped device with magnets. Quite a regular, simple to design kind of device, most conventional. And I spent some time during my undergrad, and then I did my PhD at MIT working on true tokamaks in the United States. And then I moved back to Europe. Europe has 5 to 6 times, depending on how you count, as many devices of this kind. So Europe has invested much more on the public side in this field. Now, Europe also happens to have the most advanced stellarator on the planet. Tokamak stellarators, pretty similar. They're both donuts with magnets. The stellarator is twisty. If you look at W7X, 3 characters, W7X on Google, you see the most advanced stellarator on the planet. It's in northern Germany. And in 2021, I moved back to Europe, joined the Max Planck Society, which is the organization, the national lab in Germany that hosts, that built, and now operates the W7X stellarator. And in 2022, I sort of switched from tokamaks to stellarators. There were a number of things that were happening in 2022. A key publication, the W7X going to full performance, meeting its design targets. I thought that was amazing, unexpected, and I decided I was doing the wrong thing. And I switched over, and we created Proxima at that time.
Yeah. So for you, a stellarator is probably the most efficient technology out there.
It's the most coherent, I would say.
It's most coherent. But I think for the past 70 years, the large majority of all R&D budgets and capital has gone into 2 technologies. The magnetic confinement, which is a tokamak or a stellarator, but also laser fusion. Can you just touch base upon why you think you're on the right path with stellarators versus lasers, for example?
Yeah. The two are the opposite ends of how you can do some fusion on Earth. In the laser fusion / so-called inertial confinement fusion, what you're trying to do is a very pulsed way of doing fusion. In some sense, some mini explosions. And you have to do them at roughly 10 times per second. And so one way to do it is you have a small pellet of heavy forms of hydrogen, so very light elements, and you blast them with a lot of powerful lasers. And as you were saying, the Lawrence Livermore National Lab in the US achieved a major milestone in late 2022, showing that they could blast these pellets with enough power to get a really big amount of energy coming out. Now, they did that once, and they reproduced it, showing that they really understand what's going on. This is pretty far from a power plant, I think by anyone's account. It happens over a nanosecond. You have to do it 10 times per second, and you want to do it consistently, right, to make baseload power. So I consider that to be super cool from a physics perspective, not terribly relevant from an energy production perspective. At the other end of the spectrum, as you said, magnetic confinement. Magnetic confinement is really about building a thing that is steady state, so operates continuously, and ideally is fantastically boring. We want a power plant to be boring. And what I mean by that is, from a technical perspective, I would argue this is pretty exciting, but you want a device that does not have a control challenge. You want a design challenge, maybe a manufacturing challenge, but you want this device to be fully predictable, steady, buzzing away, just like a gas power plant or a coal power plant or a fission power plant. And I think in magnetic confinement, the latest progress on magnets, on simulation, on applying computation, this is showing, and now we can integrate all the pieces, all the electronics, advances in magnets, advances in how we make support structures, steel, all of these things are coming together.
Yeah. I said earlier that you are one of the fastest growing fusion companies in the world. For your benefit, Proxima Fusion is less than 3 years old. They've already raised over 200 million, or about 200 million euros. Just a few months ago, you also announced something quite extraordinary, which is a 2 billion euro project in Germany. Can you tell us a bit more about this and why it matters?
Yeah, we've been working towards that for a while. It feels, it's just 3 years, but this was always the picture of what Proxima has been pursuing. A public-private partnership to build the Lighthouse project for Europe. We announced on February 26 an agreement with the Bavarian government in southern Germany and a utility called RWE, one of the major ones in Germany, to do a few things. One is to build a net energy gain stellarator, so a device that makes more energy output than the energy that you put in. That's a key milestone that needs to be demonstrated, but in a device here that is able to operate continuously and in a fully intrinsically stable way. So Bavaria put down 400 million of non-dilutive funding for this, and together with the Bavarian government now we are working with the German government to help us bring in extra financing, and Proxima Fusion is contributing several hundred million to that project. At the same time, with RWE, we have agreed to take over an ex-fission power plant site, so standard nuclear. There is a site in Western Bavaria that is in decommissioning, so it's ended its operation. Germany has stepped out of fission. And rather than arguing, is that a good thing or a bad thing, what we said is, this is an opportunity, let's go and transform that site into something new. And so there is literally, this big site, it's really big, and we're transforming it into a manufacturing campus, and there is a reactor hall, lots of concrete shielding, lots of infrastructure, taking out a fission reactor, putting in a fusion reactor. Sounds simpler than it actually is, but that's the plan.
But I guess there are huge benefits as well from a regulatory point of view, from a grid connection point of view as well. That's right. Should help you save a couple of years as well, no?
Best energy infrastructure on the planet, arguably, right next to the Danube River, one of the major rivers of Europe. Switch yards all over the place. Regulation is already more advanced than what we need for fusion. Fusion is intrinsically safe. There is no chain reaction in fusion, which means unlike in fission, you cannot have a runaway process. So the regulation is naturally much easier. Going to this site, ex-fission power plant site, and lowering the regulatory standard is much easier than doing the opposite way around. So we think we're saving hundreds of millions and years.
What strikes me is that fusion is now really considered a bit the new space race, right? And it's very much a race between China and the rest of the world. And it's not even about who gets to commercial fusion first, because if the Chinese get there before us, we'll catch up, and vice versa. But it is also very much about controlling critical IP in that supply chain to make sure that the supply chain will not be used as a geopolitical leverage as well. And so the approach you're taking is quite interesting as well, because you're not just building a fusion company, but you're taking a very much of a vertically integrated approach and an ecosystem approach. Can you tell us a bit more why that is so relevant to you personally to do that?
Yeah, so what I see in the US is a fusion ecosystem that is fully venture-backed. The Department of Energy in the US has done a lot. I used to be part of that ecosystem during my time in the US. The DOE has been fairly laid back, let's say. On the other hand, you look at China and you see a government that is doing fantastic work in coordinating an ecosystem, major projects, major investments coming together. There is a space in between the fully private and the fully public, which I think we have a major opportunity for in Europe. So we spun out from a national lab, one of the major national lab for stellarators in the world. And we see Europe having built so many tokamaks and stellarators, so donut-shaped devices with magnets. And we think we need to bring together that community in some sense. And that's on the academic side. On the other hand, there is the development of supply chains. If you look at a tokamak being built near Boston, so one of these donut with magnets, and you look at the pictures of the metal that is going inside that device, 80% of the metal is coming from Europe. So in precise, high precision, high performance steel structures, the European supply chains are way more advanced than the ones of the United States, and China has not yet picked that up. Doesn't mean that they won't, but it does mean that we have an advance notice, in some sense, that this is a space where we can develop, where we can win. And so, when you go to national labs across Europe and you ask them, are we going to be competitive with China on building fusion? I think a lot of Europeans are just fundamentally scared of what's happened with batteries, what's happened with photovoltaics, and that arguably is rational. And at the same time, it's absolutely no excuse to to look at our advantage today and say, it's okay, we've already lost. The Chinese are just too smart, too good.
Yeah.
I think they are very smart, and they are very good.
Yeah.
And that doesn't mean at all that we cannot win.
Because fusion is considered, who controls fusion controls the energy systems of the next centuries, essentially.
It will be a geopolitical kind of technology, not just the next market.
Yeah. So it is the most consequential technology for energy production. And by the way, it's not only about producing electrons for the grid, but there are various use cases. You can build gigawatt power plants, you can build modular power plants for data centers. But you can also use, given it's burning at 150 million degrees, you can produce a lot of industrial heat at over 1,000 degrees Celsius. And that's really important for cement, desalination, oil refining, all the critical industries we have in Europe.
Right.
And if countries like Germany, who are trying to be the first country in the world to bring commercial fusion to the grid, have a bit of an urgency, right? Because they used to import a lot of gas from Russia, that's now finished. They've shut down all their nuclear fission power plants. So there's a lot of pressure basically on Europe to reduce the cost of energy and move into fusion, I suppose.
There is a nice saying, never let a good crisis go to waste.
Yeah.
Europe is in a pretty dramatic situation on energy. We've screwed up quite a few things in line, which is remarkable. And I think when you look at fusion, how it fits in there, it's important not to just think about electricity. Electricity is a big market, arguably is the thing that everyone is screaming about across Europe, but our actual product in a fusion power plant are neutrons. Neutrons at a particularly high energy. And those neutrons mean you can enrich medical isotopes. Once you have one of these systems making 50 megawatt, not even to speak about the gigawatt, a 50 megawatt fusion power plant would make more medical isotopes than the world consumption all at once. So we can change medicine, we can change heat production, we can make high process heat, meaning at temperatures that are useful for the chemical industry, for the steel industry, not just the district heating, which is easier to deal with. Our purpose should not be understood as trying to take 100% of the grid and replacing photovoltaics. I try to highlight to people, we need to be somewhat constructive. We need to realize that photovoltaics are fantastic, they are so cheap, and we should deploy them like there is no tomorrow. Yeah. Fusion is to complement those intermittent sources. And once we get fusion, we can lower the entire cost of the energy system, not by one wand that changes everything all of a sudden, but instead by thinking about the energy system in all its complexity, in all its intricacies. Fusion can actually be that one key that enables the renewables, that enables industry to stay in Europe, but we need to be a bit faster on this.
Exactly. And I think if there are any investors in the room, the question I get a lot from my LPs is, the entire industry is targeting to get to commercial fusion by the early to mid-30s. The first pilot demonstrator plant will come as early as next year, where we're going to demonstrate Q greater than 1. So that's really tomorrow. It's not 30 years away any longer. But a lot of questions I get is, how does that fit into venture capital funds? If commercial fusion arrives in 10 plus years, how do you make it fit into? The good news is you do not need commercial fusion to happen in the next 10 years to create a lot of value and to return outsized returns for investors. There will be a lot of liquidity events on the way. A lot of companies are now listing secondaries. And there's a lot of technology spinning out of fusion as well. I'm just cautious of time, but maybe just to conclude, if you were to achieve your big vision, execute on your vision, what changes? What does the world look like?
Yeah, I would say changes in energy production across a number of domains, heat, electricity, neutrons, and so on. But maybe most important, we see our mission as being fusion, but also building a great tech company in Europe. Yeah. Proxima is bound to this continent by the know-how, the IP, the supply chains, and so on. So we see our need of developing that as an ecosystem, together with academic and industrial partners. So I think the success of Proxima is the success of our key partners, suppliers. It means that the energy cost will be lowered to the point that companies that don't even know about Proxima Fusion would actually see their costs. I like to say energy is about 5% of the GDP, but the other 95% depends on that 5%. So we think 95% is going to benefit.
Super. Please thank Francesco for coming to Athens.
Thank you.
Thank you.